excuse me, they're asking to find the dimensions that will minimize the cost. Okay, so starting off this question, we're going to first draw our cylindrical tank. Boom. Oop, that's not what I want. Okay, so that is our cylindrical tank, and they're saying that they give us 40 pi meters cubed equals the volume, and they also say that side materials, so side mats, cost $10, and top bottom mats will cost $25. Okay, so right off the bat, the first thing that we can see is that the top bottom mats are going to cost more than the side mats. Okay, so this means that we want to use less material for this top portion and use more material for the side portion, right? Okay, so how are we going to attack this problem? So this is what I'm going to do first. The first thing is I'm going to come up with an equation for the attribute of the cylinder that I'm trying to optimize. So in this case, we want to do materials, right? So that's going to be wrapping around the whole entire cylindrical shape. That's going to be creating it. So we're going to be working with surface area. So that's the component that we are trying to minimize or slash optimize or maximize. So that's what we're going to do. So we're going to come up with an equation for our surface area. So a surface area of this kind of cylinder is going to follow this. So a surface area, it's going to consist of the top two areas, right? Plus all of this area, which is when you cut it along this axis right here, this line, the sides actually unravel to become this rectangle, okay? So keep that in mind when we work on this. So, oops. Okay, so what we're going to do is we're going to come up with the formula for the surface area. So the surface area formula, okay, so for the tops, we know that the individual area, it's a circle, so it's going to be this radius times the radius again times pi, so pi r squared, and then we have two of them, so we're going to do 2 pi r squared, and then so that is for top, bottom, okay? Plus, we're going to need our side. So the surface area for the side is just going to be 2 pi RH because of that we get when we unravel it on the side. So 2 pi RH. So that is going to be sides. So when attacking these problems, you can just kind of take that surface area equation to heart. So when you're preparing for exams and stuff like that, that's basically all that you need to know. So, okay. So now that we have the surface area like this, the next thing we're going to do is we're going to add our cost analysis to it. So all the top and bottoms are going to cost $25, right? And the sides are going to cost $10. So we're going to do surface area equals $25 times 2 pi r squared, which is the top and bottom. And then we're going to do $10 times 2 pi RH, right? And then now we can simplify our equation down to 50 pi r squared plus 20 pi RH, okay? Fair. So the next thing we're going to do is we're going to backtrack a little bit, and then we're going to do what the volume means. So what does the volume mean? Because that's our given value at 40 pi meter cubed. So what can we do with that? So what I'm going to do is, I know that the volume of any cylinder is equal to pi times the radius squared times h, and h being this height right here. So that's the volume. So we know that 40 pi meters cubed equal pi r squared h. So that means that we can put h in terms of r. So h equals 40 pi over pi r squared. And then the pi's cancel out, so we're just left with h equals 40 over r squared. So therefore, right? So we'll just keep that in mind for now, okay? And then we'll move on to this. So now that we have this, we know surface area equals like this. We can replace this h right here with 40 over r squared. So now our new surface area formula is going to be 50 pi r squared plus 20 pi times h is 40 over r squared. Cool, right? So that's what we have. So I'm sorry. We also have r here, so the r's cancel out right here. So 1r and then 1r here. So our new equation looks like this. Right? So it's not the prettiest, but that's what we have right now, and that's what we're going to work with. So now I'm trying to optimize this, so I'm trying to find a minimum. So as we know, to find minimum, right, we must find critical values. So to find the critical values, first what we're going to do, I'm going to use a different color to represent this kind of solution. We're going to do the derivative of the surface area, which equals, in this case, we're going to bring the 2 to the front, so it's going to be 2 times 50 pi, so it's going to be 100 pi times r, right? And then we have plus, we can rewrite this as 800 pi times r to the power of -1 because the r is in the denominator. So we can bring that to the front, and then we have surface area prime equals 100 pi r minus 800 pi r to the power of -2. And then we can essentially rewrite that as over r squared. So just like that. So we have that now. And to solve for what our critical value is, we're going to set it equal to 0. So set it equal to 0. Just like that. I'm just rewriting it. And then I want everything over r squared. So actually, I'm going to do it like this. So I want everything over r squared, so it's easier to do the algebra. So r squared, so it's going to be 100 times pi times r squared is r cubed minus 800 pi. And then multiply this to that side, and then you're left with just 0 equals 100 pi r cubed minus 800 pi. So 800 pi equals 100 pi r cubed. Divide both sides, and then you're left with 8 equals r cubed, and r equals the cube root of this. And the cube root of 8, as we all know, is 2. So we have realized that our r value equals 2. And back above here, we know that our h value equals 40 over r squared. And our r equals 2, so 2 squared would equal 40 over 4, meaning h equals 10. Okay, so we know these values. So now we can write that our dimensions, as the question asks, right? It asks, the dimensions that will minimize the cost is r equals 2 meters and h equals 10 meters. Okay, I'm not going to circle that yet. Only reason is I want to make sure that this 2 is really a minimum. So to figure that out, I'm going to do the first derivative test. So we know that our derivative is this guy right here, right? This is our derivative. So I'm going to plug in values that are less than or equal to the critical point. So the critical point is right here too, so critical point. And then we're going to plug in from the left side into, this is going to go into f prime. So or in our case, SA prime, right? This is the first derivative test. So we're plugging it back into the first derivative. So when you plug it into the first derivative, you can do this in a calculator or manually do it. It takes a little bit of time, but you'll see that it is negative here and positive here, which indicates that if it's going from a negative to a positive, this is a minimum. So we just check that it is a minimum. So now we know that our dimensions are correct, and we can just go ahead, circle our answer. What the hell, let's give it a highlight too. And that's how you do a cylinder material optimization problem. And you can see these kinds of problems in Calculus 1, usually at the middle or end of it, and a little bit in Calculus 2. So I hope this can help you guys, and good luck.